Okay, in this lecture we're going to cover our section 3.2 material on the calculus of vector-valued functions. Now in our previous section we had defined a vector-valued function, or a vector function, as a function which takes some input variable, which we're denoting as t, and it assigns to that variable a unique vector in either the plane or in space. That is a unique two-dimensional or three-dimensional vector. And we saw in our last section that these vector functions in 3 dimensions can be used to define what we call space curves, or curves traced out in 3 dimensions. So in this section, we'll start considering some questions related to finding tangents to space curves, or evaluating derivatives or antiderivatives of these vector functions. So let's start by defining the derivative of a vector function r. So formally, it is defined just as for a real valued function. So the derivative of a vector function, which we would denote as r prime of t, is given by the limit as h approaches 0 of the difference quotient r of t plus h minus r of t all over h, provided that this limit exists. So just like we have a limit definition of a derivative for real valued functions or scalar functions, we have the same sort of definition for the derivative of a vector function. Now, as we saw in our last section, a limit of a vector function would be evaluated component-wise. So if we're looking at the limit of this difference quotient of a vector function, we're really looking at the limit of the difference quotients for its component functions, which would give the derivatives of the component functions. So we arrive at the following theorem, which gives us a simpler way to differentiate vector functions. So in general, if r of t is a 3-dimensional vector function whose component functions f, g, and h are all differentiable, then the derivative of this vector function, r prime of t, is the vector whose components are the derivatives of the component functions of r. So that is, to differentiate a vector function, you differentiate its component functions, or differentiate component-wise. So let's look at an example of this. In our first example, we're asked to find the derivative of a given vector function. And in part A, we have r of t is 4 log t, 8 root t, and t cubed. So to find the derivative of this vector function, r prime of t, we're going to differentiate each of these component functions. So the derivative of my first component would be 4 over t. The derivative of my second component function, 8 square root of t, would be 8 over 2 root t, or 4 over root t. And the derivative of our third component function, t cubed, would be 3t squared. So this would be the derivative, r prime of t, for that vector function. So let's look at another one, part B, maybe a little more complicated. So part B, we have r of t, which has component functions cosine t, e to the negative t, and t squared times sine of 2t. So here, our derivative for this vector function, r prime of t, is found by differentiating the component functions. So for the first component, cosine t, we have a derivative of negative sine t. For our second component, t times e to the negative t, we need to make use of the product rule and the chain rule. So using the product rule, the derivative of our first factor, t, would be 1, and then we multiply by the second factor, which was e to the negative t, And then we add the product of our first factor, which was t, and the derivative of the second factor, using the chain rule, is negative e to the negative t. And for our last component function, t squared times sine of 2t, again, we have to make use of the product and chain rules to differentiate. So the derivative of the first factor, t squared, would be 2t times the second factor, sine of 2t. And then we add the first factor, t squared, times the derivative of sine of 2t, which by the chain rule is 2 cosine of 2t. So let's simplify this a little bit. Our derivative of this vector function is negative sine t. Our second component, if we factor out an e to the negative t from each term, we're left with a 1 minus t. And from our, for our last component, we have a 2t sine of 2t plus 2 times t squared cosine of 2t. So this would be our derivative of that vector function. So all of our rules for differentiation might be needed in order to differentiate some of these component functions. So in part B, for the purposes of the lecture notes, let me state which rules I was making use of. I'll say by the product and chain rules, we found our derivative as follows. So let's think about a geometric interpretation of this derivative of a vector function and define a particular vector associated with a vector function called the unit tangent vector. So we saw in our last section that a vector function in 3 dimensions can be used to define a space curve. Let's call that space curve C, which again would be the curve defined by some vector function r of t. And let's take P to be some point on this curve. So the vector r prime of t, that is the derivative of our vector function, is called the tangent vector to the curve defined by this vector function r of t at the point P, provided that r prime of t exists and this derivative is not the zero vector. Now we would define the tangent line to our space curve C at a point P as the line that's passing through P and which is parallel to the tangent vector r prime of t. And we would then define a special vector called the unit tangent vector as the vector capital T of t, which would be given by the tangent vector r prime of t divided by its magnitude. So this unit tangent vector, t of t, is a unit vector which is pointing in the direction of our tangent vector r prime of t. So to illustrate this a little better, let's suppose that we have some space curve so let's say that we have some curve, I'll call it C, which is traced out by my vector function. So if we have any point on this space curve, C, let's call that point P, the tangent vector to this curve is a vector which lies tangent to the curve at that point, and is pointing in the direction of motion along our curve, or it points in the direction of the orientation of our curve. So in this example, we're moving sort of left to right, so our tangent vector at that point is going to point in the direction of motion. And of course, as we choose different points on our curve, the tangent vector, r prime of t, will change its direction. So we were defining something called the unit tangent vector as the unit vector. So that is a vector of length 1 that is pointing in the same direction as our tangent vector, but has magnitude 1. And we would define the tangent line to this curve. So here, if we're talking about a line in 3 dimensions in space, well, we have to define a point on our line, which we would associate with the point P on our curve, and parallel to our tangent vector. So we would be looking at the line in space which is passing through the point P and is parallel to that tangent vector r prime of t. So r prime of t is going to be the direction vector for our tangent line. So a little illustration of our discussion here. So now that we have these different vectors defined, let's look at some examples of these. In our first example, we are asked to find the unit tangent vector for the vector function r of t given here. So the first thing that we need to find is a tangent vector to this curve, or for this vector function. So we'll start by finding the derivative of this vector function r prime of t. So differentiating our components, we would have 3t squared, 2, and 1. So the vector which we've just found is a tangent vector to the curve, but we're asked for the unit tangent vector, which means that we need to take r prime and divide by its magnitude, or normalize this vector so that it has length 1. So looking at the magnitude of r prime of t, we would have the square root of 3t squared quantity squared, which would give us 9t to the 4th, plus 2 squared, which is 4, plus 1 squared is 1. So simplifying a little bit, the magnitude of this vector is the square root of 9t to the 4th plus 5. So for the unit tangent vector, capital T of t, we're taking r prime of t, our tangent vector, and dividing by its magnitude. So the first component of this vector will be 3t squared divided by the magnitude, which was the square root of 9t to the 4th plus 5. Our second component would be 2 divided by the square root of 9t to the 4th plus 5. And our third component is 1 over the square root of 9t to the 4th plus 5. So this capital T of t vector function represents a tangent to the space curve defined by r of t, which has length 1 at any point. So let's look at another example. In our next one, we are asked to find the unit tangent vector for the vector function r of t, given here, at the point corresponding to t equals 0. So let's start by finding a tangent vector to our curve in general, that is r prime of t. So for our first component, differentiating using the chain rule gives us 2e to the 2t. The derivative of our second component by the chain rule would be negative 2e to the negative 2t. And the derivative of our third component requires the product and the chain rule. So we would have 1 times e to the 2t plus 2 times t, e to the 2t. And we're interested in this example for the unit tangent vector at the point corresponding to t equals 0. So let's find first the tangent vector at the point of interest, that is the point corresponding to t equals 0. So substituting 0 into our tangent vector, we have 2, negative 2, and 1 for this tangent vector. But we were asked for a unit tangent vector for this function at that point. So once we have our tangent vector, we need to normalize it by dividing this vector by its magnitude. So here the magnitude of r prime of 0 is given by the square root of 2 squared plus negative 2 squared plus 1 squared, which would be root 9 or 3. So our unit tangent vector, t at the point corresponding to little t equals 0, would be given by r prime of 0 divided by the magnitude of r prime of 0. So for our first component, we would have 2/3, then a negative 2/3, and 1/3. All right. So let's look at another example. This sort of problem is very similar to problems that you saw in your Calculus 1 course for curves in the plane. So this is a tangent line problem. In Calculus 1, we often asked what is the equation of the tangent line to a curve in the plane at a particular point. Here, we're going to ask the same question, but for a space curve, that is a curve in 3 dimensions. So here we are asked for parametric equations for the tangent line to the curve defined by r of t, whose components are given, at the point 1, 3, 3. So the first thing that I'm going to do is determine what value of the parameter t corresponds to my point of interest, 1, 3, 3. So here, in order to determine what value of t corresponds to that point, I'm going to look for the value of t such that when I evaluate this vector function, whose components are given, at that value of t would yield 1, 3, 3. So setting these 3 component functions, cosine of t, 3e to the 2t, and 3e to the negative 2t, to the coordinates of my point, 1, 3, and 3, I can see quickly that t must be 0. So let me start by saying the point that we're interested in on our space curve, 1, 3, 3, corresponds to a value of t equals 0. Now, if I want the equation of a line in space, I need 2 things. I need a point on the line, which we're given here. The point 1, 3, 3 must be on our tangent line. And I need a direction vector for that line. So a vector parallel to my line, which, if we're interested in the tangent line, would be the tangent vector to this curve. So let's consider finding a tangent vector to the curve, r prime of t. So the derivative of our first component function, cosine t, would be negative sine of t. The derivative of our second component using the chain rule is 6e to the 2t. And the derivative of our third component using the chain rule would be negative 6e to the negative 2t. And we're interested in this tangent vector at the particular point corresponding to t equals 0. So let's evaluate our tangent vector at t equals 0. And we have 0, 6, negative 6 as our tangent vector to this curve at that point, which is parallel to the tangent line at that point. So we can say at this point, parametric equations for the tangent line are given by x equals, well, I take the x coordinate for the point on my line, which was 1, and then I add the first component of my direction vector, which was 0 times t. Then y is found by taking the y coordinate for my point on the line, which was 3, plus the second component of my direction vector, which was 6 times t. And z is given by the z coordinate for the point on our line, which was 3, plus the third component from our direction vector, which was negative 6 times t. So simplifying just a bit here, since our direction vector had a first component of 0, x is given by the constant 1, y is 3 plus 6t, and z is 3 minus 6t. So these would be the parametric equations of the tangent line to that space curve at the indicated point. So let's consider another problem here. We're given the curves defined by the vector functions r1 of t and r2 of t intersect at the origin. And we are asked to find the angle of intersection of these two curves. So let's think about how we might find this. So here, suppose that we have two space curves. We'll call them C1 and C2. And these two curves we can see intersect at some point. So if I want the angle of intersection of these two curves, that is the angle at that point where they are intersecting, let's think about how we could find it. So I know for any space curve defined by a vector function how to find its tangent vector. So for the curve C1, I could find this tangent vector. Let's call it R1 prime at the point of intersection corresponding to some value of t. And for the curve C2, I could find its tangent vector given by R2 prime of t at the point of intersection. And the angle of intersection for those two curves would be the angle between these two tangent vectors at that point of interest. So in order to find the angle of intersection of two space curves, we're going to find the angle between the tangent vectors for those curves at the point of intersection. So here let's start by finding tangent vectors to each of these curves. So here I'll say the tangent vectors to these curves are given by r1 prime of t, whose first component would be 3, second component is 2t, and the third component would be 3t squared, and r2 prime of t, which would be given by cosine of t, 5 cosine of 5t, and 4. So I have the two tangent vectors to my curve at any arbitrary point or for any arbitrary value of t. Now we were told that these two curves intersect at a specific point, namely the origin. So in space, the point 0, 0, 0. So we need to determine what value of t corresponds to the origin. So to find that, we could take the components of either one of these two vector functions and set all three of them equal to 0. And we see that t would have to equal 0 in order for all three components to be 0. So let me say here the origin corresponds to, which is the point 0, 0, 0, corresponds to a value of t equals 0. So I can say at the origin, the tangent vectors are given by r1 prime of 0, which would be 3, 0, 0, and r2 prime of 0, which would be the vector 1, 5, 4. So once I have these two tangent vectors, to get my angle of intersection at this point, I would find the angle between these two tangent vectors. So I need to determine the dot product of these two vectors and their magnitudes in order to use our angle between two vectors formula. So let me say, now that we have these, we can calculate r1 prime of 0 dot r2 prime of 0. So here our dot product would be 3 plus 0 plus 0, so just 3. The magnitude of r1 prime of 0 would be the square root of the sum of the squares of the components. So the square root of 9 plus 0 plus 0, which is 3. And the magnitude of r2 prime of 0 would be the square root of 1 squared plus 5 squared plus 4 squared. So we would be left with the square root of 42. Let's see if I've got that right. Square root 42. Okay. So if theta is the angle of intersection of these two vectors, then cosine of theta would be given by the ratio of our dot product, which we found to be 3, divided by the product of the magnitudes of these vectors, which were 3 and root 42. So of course this reduces to 1 over root 42. And so theta the angle of intersection between these two vectors would be the arc cosine of 1 over root 42 measured in radians. All right. So this last example illustrating how we can use tangent vectors to space curves in order to find the angle of intersection between two space curves at a particular point. So to finish out this section, we'll start talking about integrals, either definite or indefinite integrals of these vector functions. So let's start by defining a definite integral of a vector function. So here we would say the definite integral of a continuous vector function r of t, whose component functions are f, g, and h of t, is defined component-wise, just like the limit or the derivative of a vector function. So that is the definite integral from a to b of some vector function r of t with respect to t is the vector whose components are the definite integrals of the component functions f, g, and h of t over that same interval from t equals a to b. So now that we have a way to evaluate definite integrals of these vector functions, which are defined component-wise, let's look at an example. Here we're asked to evaluate the definite integral from t equals 1 to 3 of the vector function whose I component, or first component, is 2t plus 4, whose j component is 3t squared minus 4, and whose k component is 1 over t squared. So since these definite integrals are defined component-wise, we can evaluate the definite integral for each component function. So here let's consider the definite integral from 1 to 3 of 2t plus 4 dt as my I component, the definite integral from 1 to 3 of 3t squared minus 4 dt as our j component, and the definite integral from 1 to 3 of 1 over t squared dt as the k component. So finding the antiderivative of this first component function, I would have t squared plus 4t evaluated from 1 to 3 as my I component. The antiderivative of my second component function would be t cubed minus 4t, evaluating from 1 to 3 for our j component. And for my 1 over t squared, we would have an antiderivative of negative 1 over t, which we're evaluating from 1 to 3 as our k component. So let's see what we have here. For our I component, evaluating at 3, we would have 3 squared, or 9, plus 4 times 3, which is 12, leaving us 21. Minus, when we evaluate at 1, we would have 1 plus 4, or 5. For our j component, when we evaluate at t equals 3, we have 3 cubed, or 27, minus 4 times 3, which is 12, which leaves us 15. And then we subtract what we get when we evaluate at t equals 1, which would be 1 minus 4, or negative 3. And since we're subtracting that value, we would have a plus 3. And for our k component, evaluating at 3, we have a negative 1/3, minus, when we evaluate at 1, we have a negative 1, and since we're subtracting that value, this becomes a plus 1. So we are left with the vector 16i plus 18j plus 2/3 k. Or if you prefer the angle bracket notation, the vector 16, 18, 2/3. So integrating a vector function amounts to integrating each of its component functions. So we could also define indefinite integrals or antiderivatives of these vector functions in a similar way, component-wise. So let's look at an example where we might need to find an antiderivative or a most general antiderivative of some vector function. So here we have an initial value problem where we're asked to find the vector function r of t if its derivative is known and the value of our vector function at some particular value of t, namely t equals 0, is given. So here we have an initial value problem, a differential equation, which also involves some initial condition. So if I know the derivative of my vector function, r of t, I'm going to find the vector function itself, that is r of t, by taking the antiderivative of the derivative of this vector function. The same as we would do for scalar functions. So here, I'm looking at the indefinite integral of my vector function sine t, negative cosine t, and 2t e to the t dt. So I need to integrate each of these component functions. So the first two components are easy. The antiderivative of sine t would be negative cosine t. The antiderivative of negative cosine t is negative sine t. And then for my third component, I need the integral of 2t times e to the t dt. Now to evaluate that third integral, we're going to use integration by parts. So let's look at a little work for that last component. I would choose u as 2t, so that dv would be e to the t dt, and then du would be 2 dt, and v would be e to the t. So looking at this integral for our last component, 2t e to the t dt, using integration by parts, we would have u times v, which is 2t e to the t, minus the integral of v du, which is 2 e to the t dt. And we then have 2t e to the t minus 2 e to the t. So looking at our expression for r of t, we have r of t is the vector function whose components are negative cosine t, negative sine t, and 2t e to the t minus 2 e to the t. And since we were considering an indefinite integral here, that is, we're looking at the most general antiderivative of this function, we need to include a constant of integration. Now, since we're no longer working with scalar functions, we're not just adding an arbitrary constant, just some fixed number on the end of a vector function. We can't add just a number to a vector, but we would be adding a vector of constants. I'm going to call it C, but with a vector arrow above it. Or alternatively, another way that you might prefer to view this is when we find the antiderivative of these components, you could think about adding an arbitrary constant to each of these components, say plus C1, plus C2, and plus C3, which I could then group together as my antiderivative plus a vector C, where this vector C would have components C1, C2, and C3. So I need to solve for this vector C, and the way that I'm going to solve for C is by using my initial condition, the fact that R of 0 is 1, 1, 2. So using that initial condition, if I evaluate R at t equals 0, I would have a -1, 0, -2, plus some constant vector C, and I'm told in the problem statement that this must equal 1, 1, 2. That was the given vector for R of 0. So solving for C, I would have 1, 1, 2, and then I would be subtracting this vector, -1, 0, -2, which gives me that C is the vector 2, 1, 4. So for R of t, we have a negative cosine t, a negative sine t, and this 2t e to the t minus 2e to the t. And then I was adding this constant vector c, which we found to be 2, 1, 4, to that vector. So adding component-wise, well, to my first component, I'm adding 2. To my second component, I'm adding a 1. And for that last component, I was adding 4. So we have the following vector function, R of t, as the vector function whose derivative was given in the problem statement and which satisfies R of 0 is equal to 1, 1, 2.